In this next video, we're going to be looking at the banking of road curves. Alright, before we can move on to turning corners and banking of road curves, we're going to look at the forces on a car moving at constant velocity on a flat piece of road. So, when I say car, I actually don't mean car, I mean vehicle. So this vehicle could be quite anything, from a ute, a truck, a tractor, to a lawnmower. The forces acting on a vehicle moving at constant velocity on a flat surface are all going to be relatively the same. The sizes might be different depending on the mass of the vehicle and so on and so forth, but if we look at it, they're reasonably the same sort of thing. We're going to have forces acting in the way of the gravity, so we're going to have the weight of the vehicle pushing on the earth. Because of Newton's third law of motion, we're going to have a force from the earth pushing up onto the vehicle. This is what we call a normal force. So the normal force acts in the opposite direction to the weight force. So it's pushing up from the ground up. So this is our normal force. So we have the forces in the vertical direction. Now let's have some forces in the horizontal direction. We're going to have the forces due to the engine pushing the vehicle forward. We're going to get an arrow going that way, or a vector. Voila. And we're also going to have all the resistant forces. So we have friction on the road between the tyres and the road surface. So that's going to be a force that's going to slow the vehicle down or try to stop the motion as such. We're also going to have wind forces, so the drag and things like that. We've got a heap of forces that will try and stop the motion of the vehicle. So they act in the opposite direction to the forward motion. So if we draw all these vectors up, we get a lovely little picture. And, like I said, depending on what the vehicle is, you get different sizes, but they're all going to be relatively the same. It doesn't really matter too much. Okay, so we now see the forces acting on a vehicle moving at constant velocity in a straight line. So what happens if they start to turn? We have to start thinking in another dimension now. So, our car, if it's on a flat piece of road and we want to turn, we turn the steering wheel. Turning the steering wheel turns the front wheels. The front wheels then have a friction force that's causing the centripetal acceleration. So the centripetal acceleration is because of a frictional force on the front wheels that we get the car turning around a bend in a flat road. But if this car is on a banked track or a banked road and is going around a curve, it's not necessarily just the friction that's causing this. So the normal force actually helps the car move around a banked curve. So how does this so? So if we get up, picture of the old red Hilux here on a bit of an angle here going around a banked curve. Alright, so the force is acting on the Hilux. We have the force due to gravity, or the weight of the vehicle, pushing downwards. We have the normal force. The normal force is perpendicular to the surface of the road. We also have the magnitude of the vertical component of the normal force, which is going to be equal to our weight. So our weight force, or our gravitational force, is going to have the same magnitude as our Fn cos theta. If we draw in the last little vector here for our to make our diagram complete, we're going to have Fn sine theta. So we have a Fn, which is our normal force, which is acting perpendicular to the road surface. We have our force due to gravity, W is equal to mg. We have the component of the normal force, which is Fn cos theta, which has the same magnitude as our gravity force. And we have another component, which is Fn sine theta. It is possible for you to travel around a corner without relying on friction. What we rely on then is the horizontal component of our normal force. This all depends on the angle of our banking curve and the speed of the vehicle travelled. So, if we have out our formula for a centripetal acceleration and we substitute in our F equals ma, we find out that the centripetal force required is equal to the mass of the vehicle times by the speed squared divided by the radius of the curve. So, if the force required to go around the corner is provided by the horizontal component of our normal force, that means that F is equal to now Fn sine theta. So Fn sine theta is then equal to mv squared on r. So using this, we can then work out the angle required to go around this corner without reliance on friction. So if we show up our vector diagram and we find out the tan theta of this triangle we got here. So tan theta is equal to opposite over adjacent. So our opposite side is going to be Fn sine theta, so the horizontal component of our normal force, and our adjacent side is going to be our vertical component. The vertical component being Fn cos theta. So we know that Fn sine theta is equal to mv squared on r. So we can substitute that in. And we know that from our vector diagram, both the force due to gravity and the vertical component of our normal force have the same magnitude. So we can call our Fn cos theta mg. So we now have tan theta is equal to mv squared on r divided by mg. Now if we cancel out these m's, we get v squared divided by r times by g. So our final formula that we just derived, tan theta is equal to v squared divided by r times by g. Now g we know, which is 9.8 meters per second squared. R is the radius of the curve, theta is going to be our angle, and our v is the speed. So we can use this formula to find out the angle required, the speed required, the radius of the curve, all knowing some other information about it. So to see how we use this formula, remember, LiveScribe PDFs. So the key points from this video. The forces acting on a vehicle which is moving at a constant speed in a straight line are balanced because the vehicle is not accelerating, it's maintaining a constant speed. The forces of this are the normal force, which has the same magnitude as the force due to gravity, the forces of the car engines pushing it forward, and the forces of drag and friction causing it to balance out the driving force. In a bank curve, we have the force due to gravity, the normal force, we have the horizontal and vertical components of this normal force, because remember, the normal force is perpendicular to the road surface. Using the horizontal component and the vertical component of this normal force, we can derive the formula tan theta is equal to v squared on rg. You need to make sure you know how to do this. And you need to be able to use the formula tan theta is equal to v squared on rg. So you can see that in the LiveScribe PDFs. So that is it on centripetal acceleration and uniform circular motion.